Good morning, everyone. My name is Longhao Qian. So I'm going to give you two lectures for 1216 on quadrotor dynamics and control. Okay, so I'm a postdoc fellow from the Flight Systems and Control Lab. Okay, so my supervisor is Professor Hugh Liu. So I bet you have already met this professor, and he is also the supervisor of this course. So my office is at room 134. So if you have any questions regarding quadrotor dynamics and control, so feel free to come drop by. And also, if you have any further questions but you are not able to be here in Caius, you can always send an email to me. I'm more than happy to answer your questions. Okay. And so feel free to visit our group website, YouTube channel. There are many interesting videos talking about our research. So maybe you can get some ideas about your future career and research directions. Okay. Okay. So here are the members of our team. So that's two group photos showing the members from last year to this year. So here is a picture of our office, our experimental room, so which is called the OptiTrack room. So where we do all the drone research inside this OptiTrack room. We also have a flight simulation, flight simulator. So the flight simulator is in our flight simulator room. So you can, so in this room we do some research regarding the fixed-wing aircraft, as well as the research related to human controls. Okay, so this lecture is part of the career program. So it's the acronym for Center of Aerorobotics Research and Education. The purpose of the lectures I gave here is to give you a fundamental idea about how to design and build a UAV, especially quadrotor and multi-rotor. So this is an outline of this course. So there are two lectures about the quadrotor dynamics and control. Today I'm going to give you an introduction, some basic concepts about quadrotors. After that, I'll go through the basic dynamical modeling as well as how to do linearization based on the nonlinear model. Okay. So in next week's lecture, I will cover position stabilization control as well as path following control. And at the end of the course, I'll give you some ideas about how to set up a commercially available quadrotor. This is for to complete your project. Okay. So any questions so far? Good. Okay, so we begin with the first section. It's the motivation. So why do we need to use quadrotor or multi-rotors? The reason is very simple, right? Because the main advantage of such vehicle is that they are able to take off and landing vertically without any airfields. So it's very good for completing certain tasks. In addition to the vertical takeoff landing capability, it is also very mechanically simple. So there is no very complicated aerodynamics. All you need is just a flight control unit with some motors and propellers. And by the digital controller, by implementing a digital controller, then you can facilitate all kinds of flight and tasks. In addition to those advantages, it's also highly maneuverable. So if the thrust to weight ratio is high enough, this quadrotor can do very aggressive maneuver, such as the quadrotors in drone racing, and also all the drone racing and all the acrobatics in the drone show. So the main characteristic of such a flight platform is that they have rigid frames. So all the propellers are attached on the rigid frames. So other than propellers, there is no moving part. Usually 4 or more rotors and propellers are used to control the motion of the quadrotor. So each motor can be controlled independently. So the entire motion of the vehicle is totally controlled by varying the speed on each rotor. So by varying speed, you can control the attitude, and control the and then you can control the thrust. So basically, you can control the entire motion of this platform. Okay. So the history of quadrotor dates back to right now it's exactly 100 years ago. So by this Russian American George Bokzak. So he designed this very large human in-the-loop quadrotor, as shown in this picture. So in his early design, it already resembles some of the key features of the modern quadrotor. So you have so here we have a 4-arm with 4 rotors, and each rotor has 6 blades on the propeller. But during that time, this kind of design is not widely used because the quadrotor or multi-rotor is inherently unstable. So the poor stability and the requirement of advanced control algorithm limits the usage of such aircraft in the old days. So later, during 1950s and 1960s, so with the development of digital controller, people are able to control this kind of very unstable aircraft, such that they can be used in commercial, both commercially and military. Okay, so nowadays, we can see a lot of applications of multi-rotors and quadrotors. So here are some projects that has been done in our group. For example, we use the drone for agricultural and environmental inspection. So this is a figure showing that we use this multi-rotor, and the research is mainly about designing a planning algorithm such that the drone can scan the area to detect the unhealthy vegetations. And also the planning algorithm ensures that we can do the scanning with minimum battery change. Okay. So in addition to the surveillance and agricultural inspection, the quadrotors and multi-rotors are also widely used in payload delivery. So this is also a previous project done in our lab, where we use multiple drones to cooperatively carry a large payload. So to increase the payload capacity of such systems and enable future usage of this drone in urban mobility. Okay. So here are some additional examples. Recently, one of our team members completed a vision-based tracking based on the quadrotor drones. And because this quadrotor drone is very agile, later we are going to use this vision-based tracking algorithm for drone racing. So as you can see, the drone is going to move transverse very fast through obstacles, such that it can be used for some real-world applications. Okay. So in addition to that, there are many other applications such as filming. A lot of films are shot by using drones. And also in the near future, there may be a quadrotor or multi-rotor passenger flight. Okay. So that's pretty much about why do we need to use quadrotors. So why control? So is anybody here familiar with the concept of of stability and instability? Good. Do you know the difference? So what's the difference between a system to be stable or unstable?
Stable is like the system being stable, but
Yes.
unstable can still fluctuate into a stable state.
Good. Yeah. So being stable means that see this we have this particle on the lowest position of this ball, right? So if there is a push if there is a tiny push, that is, so to cause the particle to move away from the equilibrium, then naturally this system turns towards the equilibrium. So it has a tendency to go back to equilibrium after some disturbance. But being unstable means that, okay, it's like a particle on top of its ball. It's a sphere. Okay? So if we have a push, it will just move without a stop. So it will move away from the equilibrium and without getting back. So that's the basic idea of about being stable and unstable. So the quadrotor is unfortunately is an inherently unstable system. So that's what is the key reason why the control is very necessary for such systems. It is very different from the fixed wing aircraft, where you have a statically stabilized pitch and the roll channel. For quadrotors, if there is a tiny push on the system, such as the wind gust or some parameter uncertainty or some vibrations on the frame, then the quadrotor will just keep rotating. So if there is no control algorithms, no any other control method, this system will just keep rotating. And because it rotates, the lift will have a horizontal component. So by rotating, the lift will actually drive the system away from the equilibrium without coming back. So that's the key reason why we need to use control on such a quadrotor and multi-rotors. Okay. And so this is animation showing that the systems. So on the right, the quadrotor is. So there is no control on the quadrotor on the right. So as you can see, the moment that it takes off, it just moves away from the desired position. And with the control, it is able to stabilize at our given position. Okay, so any questions? No? Good. So in terms of facilitating such a control, there are two main ways. So the first way is to manual control. So basically, it is about using a human pilot to actively control the drone. So after some training, a human is able to control the drone. So when the operator is control the drone, his or her eyes acts as a sensor to measure the position and velocity of the drone, and the brain calculates how I'm going to command this drone to move either backwards or forward, and then the brain sends signal to the hands so that we can apply such control through the remote transmitter. So, for automated tasks, we need automatic control. So in this case, there is no need for human intervention. The sensing part, for example, indoor task, the sensing part is completed by some external sensors. So here is a typical sensor we use during our experiment. It's called the OptiTrack system. So it basically consists of several cameras. Okay, the camera here, so we have a group of cameras. So the cameras will take pictures of our drone and extract some markers on the drone to localize the system. And then all the localization information will be gathered, and we will do post-processing, such as filtering, velocity estimation, and then we'll gather and all the information is going to be put on this ground station computer. And the ground station computer later sends out the feedback on the position measurement, on the velocity measurement through the Wi-Fi network to each drones. And on each drone, there is an onboard computer which processes this information and then calculates the control command and send it to the lower HCU. So this is a typical framework of how to do automatic drone flight as well as automatic control while doing experiment indoor. So for outdoor experiments, the principle is the same. So we still need a sensor. Okay, So we still need a computer on the aircraft. But the sensor we use now is not the OptiTrack. Instead, we use GPS. So normally GPS, and also there are some people using vision-based such as cameras or lidars. So in outdoors, we use the other kind of sensors, but the principle is that those sensors will give us position and velocity measurement, and they can be used as our feedback control input. So to sum up, so why do we need control? Because the aircraft is inherently unstable. And also, if we have control on board, we can facilitate a high-level tasks such as delivery, scan, surveillance delivery, and some drone racing on top of this automatic control framework. Okay. So, questions? Good. Okay, now I'm going to talk about the principles, some basic concept principles about the dynamics of the quadrotor. So, the quadrotor, as you can see, is actuated by 4 propellers. So the spinning of the propellers creates a lift on the system. So the key principle here is that if we can manipulate the lift on each propeller, then we can manipulate the torque, the net torque, and the net lift force on the platform. For example, if we want the drone to hover at this position, then we need the force on each propeller to be exactly exactly a quarter of the total gravity force. So I think Professor has already covered a part of this, right? So in order to do the propeller modeling and motor modeling, typically we use a so-called UIUC database. So is everybody familiar with the database? Good. So if you if you're able to calculate an advance ratio by using the free stream velocity as well as the propeller spin RPS, then you are then based on those experiment data from the data set, you can get the CT, CP, and CQ. So basically all the coefficients of propellers. So is everybody familiar with KDE motor data set? No? Okay. So this is also a website where you can get the characteristics of electric motors. So for example, you can go to this website and it tells you the kV value, the inner resistance, and also all the response of the voltage, and also the response between the voltage and the spinning velocity. So what we do is that if we have a propeller chart from the US database and the motor characteristics from the KD database, then we can do the modeling of each individual rotor. So here is how we do the motor model. So although the main majority of motor used is brushless. So, but during the modeling process, you can still assume that you use a brush DC motor. And the principle of modeling such a system is that you have a resistance. So this is the diagram of the circuit. And this R is a resistance, the L is an inductance, and the EB is so-called back EMF. So what you do here is that if you have an input voltage U, the U will actually drive the current in the within the circuit. So it equals to the voltage drop on the resistance, the voltage on the inductance, and the back EMF. The back EMF is a function of the rotating speed of the propeller. So when the rotation speed is low, you have a relatively low back EMF. So in this case, you will have a higher current. So then it will accelerate the propeller. But when the propeller spin at a very high speed, the back EMF is relatively low, so you have a low torque output. And the torque on the propeller will eventually balance the torque from the motor. So this is how you reach a torque balance for this motor propeller combination. So, any questions about this? It's clear? Okay. And also, the modeling of a propeller is simple here. So unlike fixed-wing aircraft, where the free-stream velocity is usually assumed as your forward velocity, for quadrotors, this velocity is the velocity that is perpendicular to the disk. So if this is the forward velocity, then the velocity perpendicular to this is this component here. But usually, when we do experiments, and in terms of control, we do a further simplification. Is that we assume that this velocity is very slow, is very small, so we assume that this v is approximately 0. So in this case, we assume that the advance ratio in terms of a drone study, a quadrotor study, is relative. Yes.
Yes, I was just wondering. So the formula is there for the UIUC database. This is something we ran into some of the other questions.
Yes.
Therefore, the prop forward, whereas when we look at hover and uses a helo, we had to translate the formulas around.
Yes.
So,
yes.
So we would still do that here for these, correct? Like this is just the individual prop we're looking at.
Yeah. So good question. So we are calculating the performance of the quadrotor. So if you want to do a little bit of detailed study, you still need to do this velocity. You still need to calculate the velocity component that is perpendicular to the. Sorry. So draw this. So if this is a rotor disk, right? And if this one is the forward velocity. So in terms of performance calculation, you still need to get the perpendicular component so that you will have an accurate estimation of the J. But in terms of control, we do another simplification. Yeah. So we just assume that this J is 0. And any other uncertainty caused by this approximation is handled by the controller. So we just treated the unmodeled dynamics as part of the disturbance. So any questions regarding this issue? Good. So by this simplification, then based on the UIUC database, we can directly get the CT, the CP, and also CQ from the database. So basically here, CT, CP, and CQ are just constant. So we'll have 3 constants that models our propellers. So based on the calculation of the torque from the motor and the torque estimation from the propeller, then we use this model. We'll use this model here. Then you will eventually be able to calculate the steady state propeller spinning velocity. So you'll get so at a given voltage, you are able to get the spinning velocity of the propeller. And in the end, you are able to get the thrust from the propeller. So another thing here is that if CT, CP, and CQ are constant, and we can see here, it is a function of the square of n. So in the later lectures, we just assume that both the torque on each individual rotor and the thrust on individual rotor is a quadratic function of the rotating speed. Good? Because CT, CP, CQ here are constant. And this is a quadratic formula, a relationship between the RPS and the thrust. Good. So once we get the thrust, the formula of calculating thrust, in this very simplified hover case, then we can do estimation and also calculation about the desired rotor spinning angle, spinning velocity. So basically, it's very simple, right? So the thrust on each rotor is a quarter of the total gravity. And then by using this formula, and the Kf is a function of the Ct. You just get from the UIUC database. And then in the end, you can figure out the omega. Yeah, so you can calculate, you can backtrack and get an estimation of about the omega. Okay. So here's a bit more explanation. So during hover, the force will have a force balance, and the moment here during the hover, the resultant moment or the net moment should be 0. So right now, now you are facing an issue about it. So if I want to get the lift on each individual rotor, I only have 2 equations. So one is the force equation, one is the torque equation. Then how do I get how do I solve for this? How do I solve for the lift on individual motors? Because we have 4 unknowns. Well, I will talk about this in later slides. It's called thrust mixing. So here I will explain a little bit more about how to control the attitude. So this is very simple, right? So if we increase the force on one propeller and decrease one on another propeller, it will create a net moment. So basically it tilts the quadrotor. So when the quadrotor tilts, then the total lift has a horizontal component. So we're going to use this lift to control the position of our quadrotor. So and this is a complete process of how to about how the quadrotor moves from one spot to another spot. So initially we start from this hover position where we have 4 equally where the lift on all propellers are equal, and then we increase the lift on the propeller that is away from the desired location. So we increase the propeller on the right a little bit. We decrease the lift on the propeller on the left a little bit. So that will create a net moment. And because of this net moment, the quadrotor will tilt a little bit to create a net force, a horizontal force to accelerate the quadrotor. And then the quadrotor will gain a horizontal speed, so it moves sideways. And when it is about to reach the target location, so the quadrotor, so we do the same process, but in the mirror, reverse, or the mirror version. So we increase the thrust of the rotor on the right, and then we decrease thrust of the rotor on the left. So it tilts backwards, so that the lift has a horizontal component to decelerate the quadrotor, and eventually it will come to a stop. So this is the process of how to control the quadrotor to do a horizontal move. It's more like a tilt, move and a tilt, stop. So any questions? Good. So what about yaw control? So if we want to control the yaw, we need to control the torque directly. So basically, if we want to control the yaw, we need what we need is that we need to increase the spinning angle, for example. So we need to increase the spinning angular velocity, say omega-3 and omega-1. So if we increase the spinning angle of these 2 propellers, it will increase the moment. It's basically a drag, right, on the propeller to the quadrotor. So it will have a resultant drag in the opposite direction. And similarly, if we decrease the rotation speed of omega-4, so omega-4 and omega-2, then the drag on this propeller will decrease because the spinning velocity decreases. So the net torque result from these 2 propellers will decrease a little bit, and it's in the opposite direction. But the direction is in the opposite direction, but the magnitude is a little bit lower. So now we have a resultant yaw torque on the quadrotor. But since we increase the spinning angle of these two and spinning velocity on these two propellers, and we decrease spinning velocity on these two propellers, the net lift is the same. So in this case, we can keep the quadrotor at the same place while rotating, while doing the yaw control. So, any questions about this? Good. Okay, so now we come to the formula of how to get the propeller spinning velocity when you are given the desired lift and desired torque in three-dimensional directions. So here is a simplification here. Since we assume that the advance ratio is 0 in our case, so CT and CQ are constant. So we use the kappa here to denote the ratio between CQ and CT. So this basically means that the torque is a linear function of our lift. Okay. So by using this simplification and this linear relationship, we have the following formula. So this is called a thrust mixing formula. So this F is the desired lift. So it's like a total lift on the quadrotor. The tau here are the total moment on the quadrotor. And this F1 to F4 are the individual lift on each individual propeller. So here is a formula. And if we write it into a linear relationship, so basically a linear matrix times the F, where F is the vector consisting of 4 lifts, then we can see that we have a linear relationship between our target force and each individual force on rotors. So here L is the length of the arm of the quadrotor. So I will explain further a little bit further. So here is a diagram showing the geometry of a quadrotor. So this length is L, right? And since we have we only have 4 rotors, so the arm, so because we have a lift here, so it creates a moment around the center of mass, right? So the arm here is square root of 2 over 2 L. So the moment created by this rotor is F1 times square root over 2L here. So so this basically corresponds to this term here. So any questions? So basically we calculate the moment around the y-axis for individual rotors. Okay. So similar for F2, is it also the same? Oh, sorry. It's not here. It's this one. So yeah. So this arm corresponds to torque around the y-axis. Sorry. So if we want to calculate the torque on the x-axis, then we need to use the arm projected on the y-axis. So this is also square root of 2 over 2L. And as you can see, this times F1. And the F2, for F2, the torque, the arm is in this direction. However, because F2 is on the right side of x-axis, so it creates a negative torque. So the torque created by F2 around the x-axis is F2 times square root of 2 over 2L. But we have a minus sign here. So that's why we have a minus here. So a question about how to about the torque calculation. Good. So basically, then we do the same for all the propellers, right? So then we arrive at this formula. The first one is simple. It's just a combination. It's a summation of all the lift force. It's the total lift. And the last one is that because we have this simplification. Because we have this simplification here, saying that okay, the torque of each rotor is a linear function of the lift. Then the net torque around the z-axis is a torque on is actually the torque on each rotor, but as a function of the linear function of the lift. So, for example, if the rotor number 1 spins in this direction, it creates a positive torque, and the rotor number 2 spins in opposite direction, then it creates a negative torque. And the combination of the 4 torques is like the total yaw-in moment. Good. And also, so as we can see in the previous slides, this can be written as a function, as a matrix K times the F, right? So when we have a desired F, is that the moment and the lift we want the quadrotor to have, then by inverting this matrix, we can get the lift on individual rotor. And then by this quadratic function, by using the simplification, then we can resolve for each the angular velocity on each rotor. Okay, good. So after that, so the overall control strategy for such a system is something called a nested control architecture. So basically, it says that the control is modularized. So we have something called an inner loop and outer loop. So then each loop consisting of it's going to be responsible for certain tasks. For example, if we want to control the motion of the quadrotor, we need to control the motor speed, right? So this is kind of an inner loop, mostly inner loop. And on top of that, in order to control the angle, so where the rotor points or where the quadrotor points, we need to control angular velocity by varying the speed of each rotor, such that it will create a different thrust, resulting different moment to rotate this quadrotor. So once we have the angle control and angular velocity control, and then it means that we can control the lift. So we can assume that there is a force in 3-dimensional that we can assign arbitrarily. And finally, if we can control the total force on the quadrotor, it means that we can control the position of the quadrotor. So it's basically, if we want the quadrotor to move sideways, we just what we want to do is just we tilt the lift a little bit, so it will move sideways and then stop at a given location. So this is called something called the nested control structure of the quadrotor. So it's the main control framework used in quadrotor and multi-rotors. Okay. So I have some questions for you. So as we can see, how many degrees of freedom are there? So we have 6 degrees of freedom, right? So we have 3 translational channels. We have 3 rotation channels, right? But since the problem is that we only have 4 motors. So this is a very typical under-actuated system. So the thing is that is it possible that the quadrotor hovers at a given position while have a tilt angle that is not 0? So is it possible? So why? Yeah. Yeah, good. So for this system, because it's underactuated, so we cannot freely assign all the states. So we can only say we can only determine say okay, we want to get this the system to a given position, but attitude. But for the attitude, we do not have any controls. Right. Good. Any questions so far? Good. Okay, so now I move to the dynamic modeling of such systems. So previously we covered the thrust and the basic concept and how to get the thrust and motor and the modeling of each motors. Then it's more like a mathematical model for the aircraft itself. So before we talk about the details of the dynamics modeling, there are it's essential for us to get a little bit understanding about the coordinate frames. So for aerospace, in aerospace applications, there are two main frames used. So one is called the ENU frame, is east north up frame, and NED frame is the northeast down frame. So ENU frame means that your z-axis is pointing to the sky, right? So this one is up, and the x is pointing to the east, and y is pointing to the north. Okay. AED, on the other hand, the direction is pointing towards the earth, and the x is pointing towards the north, y is pointing towards the east. So we are doing your work, so be careful of the systems about coordinate frames. So okay. For fixed wing study, for all the frequency, people tend to use the NED frame. But in quadrotor study, people use both. So some people use NED, some people use ENU. So make sure you figure out the definition of coordinate frame before you move to the math. Okay, so we start with a simple model. It's called a planar 2D quadrotor model. So this is the y-axis, and this is the z-axis, and this phi is a rolling angle here. So as we can see, so we are because of the thrust mixing algorithm we are able to control the total lift F and the total torque tau on the quadrotor. So if we get the total F and total tau, then we have a way to transform into the spinning velocity of each rotor, right? So this is covered in previous slides. Okay. So in the later slides, I will just use F and tau as our directed control input. So for this 2D case, as you can see here, F is pointing upwards, but it's perpendicular to the frame of the quadrotor. So, and we have a gravity force here, right? So in this case, we denote F as U1. So it's our first control input. And the tau is the U2, is our second control input. Okay. So then as you can see, this equation describes the horizontal movement of the quadrotor. So basically Newton's second law, right? This is acceleration. This is the force. This is horizontal projection of this force. This angle is the phi. So as you can see, because it's pointing towards a negative direction of y, we have a negative sign here. But the amount of magnitude is determined by the sine phi. Okay. Z double dot denotes the movement in the vertical direction. So very simple, right? So we have a minus g here, denotes the effect of the gravity, and the vertical component of this cosine phi, denoted by cosine phi, is a vertical component of the lift. So if we write this in the matrix format, is it is showing here. So basically, we have this sine phi times u1 cosine phi times u1. And for the rotation channel, it's also simple. So we have the angular acceleration, phi double dot, controlled by the u2, and also divided by the moment of inertia around the x-axis. So this is an equation of the motion of the 2D quadrotor. As we said earlier in slides, the dynamics of this system is very simple, right? So the problem is to design a controller such that this thing can stabilize in the air. Yes.
What if the x-axis is just a
This is a 2D case. So the x-axis is pointing outside of the screen. So yeah, so
When you see double dot, we're talking about acceleration.
yes.
Because in fixed wing, we usually do it using velocity. So is that a difference?
For acceleration, it's always double dot, right? But I think in UAV, because many forces depends on the dynamic pressure, so that's why you have velocities in the force. Good. Any questions? No. Okay. Okay. So then we write the entire system into a so-called state space format. So the entire state consists of the position is the P, and this is the V. So the entire state consists is in the position as well as the attitude of the quadrotor, and also the velocities of the quadrotor. So then the x dot equals this, and as you can see, the later half of the state space equation is exactly the same as the equation we got from the Newton's second law. So basically, we write this is a complete format. Okay, any questions? Good. Okay, 3D case is a little bit more complicated. So, but the principle is the same. We still need to figure out the lift. The D here is a drag, so in our case, you can just assume it's 0. We do a simplification. And also G is a gravity force. But right now here, instead of using the angle, the trigonometric angles, we use a rotation matrix. So RIB is a rotation matrix from the body fixed frame on the quadrotor to the inertial frame. And the E3 is a unit vector pointing towards the z-axis. So as you can see, this Fi just basically means the lift force in the inertial frame. So the from inertial frame and plus the gravity in the inertial frame is the total acceleration of the aircraft. So it's basically the same. The only difference here is that we use a rotation matrix. And the rotation motion is a little bit complicated because it involves the 3D rigid body dynamics. The acceleration here is caused by this total torque, tau b. And the J is the moment of inertia. So basically, J is an inertial matrix consisting of the IXX, IYY, and IZZ. And the omega b is the angular velocity of the quadrotor. So this one is also the Newton's second law, but in the rotation channel. Okay, and then finally, this is the kinematics of the coordinate frame when you have angular velocity. So basically, the time derivative of the omega, the r, is a function of the previous r and your angular velocity. So this, because this is an introductory course, so I'm not going to cover too much of details. But if you are interested in rigid body dynamics, so I provide several useful references that you can read afterwards. Okay. Good. Any questions so far? Okay, that's pretty much for the dynamics modeling. And the next big part is linearization, which we're going to use for the later controller design. So is that anybody here already familiar with linearization? Anybody? Yes? Okay. It's one? Okay. We have several people that are familiar with this idea. Okay, good. So the concept of linearization is that the original system, as we can see from our previous modeling, is a nonlinear system. So designing a control law directly for nonlinear system is difficult. So instead we resort to a simplified case by analyzing something called infinitesimal variation. So for a system of x dot equals f as a function of x and u, if it is at the equilibrium, so if the equilibrium is denoted by x naught and u naught, which means that if we plug in x naught u naught, this f should be 0. It means that at this point x dot is 0. So this is the definition of equilibrium. So at this point, nothing moves. Okay. So then, what if we have a little bit small deviation from the equilibrium? And according to the calculus, right? So we have Taylor expansion, right? So if the deviation is small, then we can approximate this effect of the small deviation by using the first order approximation. Basically, it means that we use a Jacobian of the function. So as you can see, if the delta x here is a small deviation from the equilibrium, then the resulting dynamic equation is approximately, not strictly, in this format. So we take the first order derivative with respect to x, and times the small variation of x, and the same for the control input. So we have first order derivative with respect to u times the small variation of u. So by doing this, effectively we converted the nonlinear system into a linearized system in this format. So here A and B are two matrices. So matrices. Now, as if the system is a linear system, then we have abundant tools to build a linear controller to stabilize the infinitesimal variation. Okay. So any questions? Good. So then, how do we apply this linearization on the planar 2D model? So I use the planar quadrotor model as an example. So this is our previous equations of motion here, right? This is a total state, and this is a total system. So basically, this one is fx and u. Okay. So then the first step you need to do is to rewrite the total state by using something called indexed. So by using the indexed interest, it is for later for you to better calculate the Jacobian of the system. So here means that y corresponds to x1, and the z corresponds to x2, and so on and so forth. Right? Phi dot is x6. So then we can rewrite the entire formula into this format. So this is the original equations of motion, and this is an equation of motion using this indexed format. So we have x4, x5, and x6 as the first three elements, and these terms are from the previous equations of motion. And here, x3 is phi. And then what we do is that because the f is a multi-variable, it's a multi-dimensional function, So the first element of f is f1, second element of f is f2, and so on and so forth. So right now it's more like in a very normalized standard format. Okay. So then we need to calculate the Jacobian of the system. So the Jacobian is a matrix, as we've seen previously, right? So the i's and j's component of this matrix is denoted by this thing ij, which means that you take the derivative of fi with respect to xj. So, for example, if we want to calculate the Jacobian, so fi j. So, for example, if we want to calculate the element on the first row and the second column, what we do is that we take a look at the function at the first column, and we take the derivative of this function with respect to x2. So same here. So for example, the first row of this Jacobian is in this format. So it consists of 6 elements because of our 6 states. And each element here is calculated by using this format. So for example, the first element of the first row is partial f1, partial x1. But as we can see here, this function has nothing to do with x1. So the first entry is 0. Right? And also so on and so forth. So for the second entry, it's also 0 because it does not contain anything related to x2. And also the same for the third element, which is also 0 because it has nothing to do with x3. So on the fourth element is 1 because it contains only x4. So partial f1, partial x4 is 1. And also similarly for the x5 and x6, the Jacobian here is 0. So any questions about how to calculate Jacobian? Good. Yeah, so we do a similar calculation for all the remaining rows. For example, f2 for partial x, the second row. The result is in this format. So because it's only related to x5, yes. Oh, okay. Yeah, so it's simple, right? So we just follow the similar formulas and go through, then we're able to get the Jacobian down. And for the fourth and fifth and sixth row, you only need to take a Jacobian that corresponds to the actual formula in the dynamic equation. And then finally, you write the Jacobian in this matrix format. Okay, and then we can do the similar operation for partial f, partial u. Good. Okay. So finally, after obtaining the Jacobian, because right now Jacobian is a function of the x, so in order to get a linearized equation of motion, we evaluate the Jacobian at the equilibrium. So we just plug in x naught u naught into this equation, and then the resulting A is in this format. Okay. Any questions? And the same for the partial I, partial u. So we get the B matrix by plugging the equilibrium to get the B matrix. So that's pretty much the steps of about how to do linearize the control. aside from doing this by hand, you can also do this by using MATLAB symbolic toolbox. So it provides an easy way for you to do the linearization for complicated systems. So the step is that what you do is to define your states x, u as MATLAB symbols using the sim function. And the key here is that you declare a MATLAB function by using the symbols in this format. So this basically corresponds to the equations of motion, as you can see here. So then the third step is to call the Jacobian function in the MATLAB. So it will automatically calculate Jacobian for you. And then finally, you declare the resulting symbolic function into a MATLAB numerical function. It's called f. So by using the MATLAB function command. And then you can plug in x and u to get the actual value of a and b. So, okay. So this is a final result of the MATLAB symbolic calculation. So as you can see, this is our original result from our hand-derived equations of motion, and this is the result from the MATLAB symbolic toolbox. So give you the results for you to double check for the results. Okay. And also, after plugging the numbers, it gives you exactly the same result. So another way to do is that you can also use a Simulink to get the linearized model. So whether you build the model in Simulink by using blocks. So those blocks determine actually constructs equation of motion here. So for example, this one is those three elements, and this sine function here denotes the horizontal force, and the cosine here denotes the vertical force, and finally this one determines the moment on the rotation channel. So the key here is that you define a input and output, so that it can be used by this function called limod. So basically, here what you do is to add your name of the Simulink, and input the x naught and u naught in the Simulink, and then will automatically calculate Jacobian for you. So that's how you get the linearized equation of motion if you have a nonlinear motion.